Alright, in this video we're going to introduce the concept of buffer solutions. If this is the first time you're seeing this, then pause the video along the way and take down notes. If it's used as a review, then I'd suggest you pause the video and try the problems yourself as we get to them. So, a buffer solution. To buffer means to resist a change. So a buffer solution is a solution that resists a change in pH if you add an acid or a base. Normally, if you add an acid to a solution, like pure water, or to a solution of weak acid or a solution of base, the pH will drop, and it will drop usually quite dramatically. If you add a base to a solution or to pure water, the pH will rise, and it will usually rise dramatically. But when you add the acid or base to a buffer solution, the pH changes very little. Okay, the buffer does not totally prevent change in pH, but it really resists the change in pH. The reason for that is that buffers contain mixtures of weak acids and their conjugate bases. So if you have a buffer in an acidic pH range, it'll have a weak acid with the salt that contains its conjugate base. Or they may be basic buffers, so a buffer at a pH above 7, which would contain a weak base and the salt of its conjugate acid. So notice that buffers always contain weak acids and weak bases. So now when you add an acid to the buffer, the base that's in the buffer will neutralize the added acid. If you add a base to a buffer, the acid that's present in the buffer will neutralize the added base. So buffers can resist changes in pH because they contain mixtures of weak acids with their conjugate bases, or weak bases and their conjugate acids. Suppose we want to calculate the pH of a buffer solution, and we're going to make this buffer solution by dissolving 10 grams of sodium acetate. So there is the salt that contains acetate ion. Acetate is the conjugate base of acetic acid, and sure enough, we're dissolving it in 500 mils of 0.1 molar acetic acid. So here's a weak acid with the salt that contains the conjugate base. We'll assume that the volume stays constant. There's a couple of ways to calculate this pH. One is to do what's called a common ion effect problem. Let's quickly set that up. Common ion effect can be done either starting with the conjugate base or the conjugate acid. I'll start with the acid for this. So you basically just want to set up the weak acid weak acid dissociation reaction. So the weak acid ionizes in water, and it produces hydronium ions and its conjugate base. You could also have set up the weak base ionization reaction. The weak base reacts with water, producing hydroxide ions and the conjugate acid. Either one is fine. Now we're going to fill in this ice table using the concentrations from here. So the weak acid starts off with 0.1 molarity. The water is a liquid, so we'll ignore it. The hydronium that's present in the solvent water is so small that we'll ignore it. Now I'm going to quickly calculate the concentration of the base. We have 10 grams of sodium acetate, so let me just do that up here. 10 grams sodium acetate. I'll get rid of the grams and I'll switch to moles, and then I'll divide that by the volume in milliliters, and then I'll get rid of milliliters and divide by the volume in liters, divide by liters. So now when I'm done, grams will cancel, mils will cancel, I'll have moles per liter, I'll have the concentration of the salt. So this is the molar mass. 1 mole weighs, and let me just calculate that. So sodium 22.99 plus 2 carbons plus 2 oxygens plus 3 hydrogens. So 1 mole weighs 82.04 grams, the molar mass. The volume was 500 milliliters, and there's 1,000 milliliters in a liter. So 10 divided by 82.04, this is how many moles we have, and then when we divide by the volume, we end up getting a concentration of 0.244 molarity. Right? Now that's the concentration of sodium acetate. In that formula we see only one acetate ion, so therefore when it dissolves it's going to produce 0.244 molar sodium ions and 0.244 molar acetate ions. So we have 0.244 molarity acetate initially. And now the weak acid ionizes, and we end up getting 0.1 minus X, X, and 0.244 plus X. So now we can set up the Ka expression. The Ka for acetic acid is 1.8 times 10 to the minus 5. You can find that in a Ka chart. That's going to equal the X value here. I'm being a little lazy not writing out my equilibrium expression, but X times 0.244 plus X over 0.1 minus X. And now you can find X using either the approximation method or using the solver on a calculator. I'll quickly do it using the solver on the calculator. So I'll press the math button, 0. I'll go up to clear the previous equation. So we want X times 0.244 plus X, close the bracket, divide by 0.1 minus X, close the bracket, and then minus 1.8 times 10 to the minus 5. We give 0 as a guess. We're saying the answer is going to be close to 0. Alpha solve 7.4 times 10 to the minus 6. And that's my hydronium concentration. Therefore, the pH of this solution will be the negative log of that, negative log of 7.4 times 10 to the minus 6, 5.13. Now there's another way we could have calculated the pH of the buffer, and that would be to use what's called the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation starts with the Ka expression for the acid. Ka is equal to concentration of hydronium times A minus the conjugate base over HA. And by taking the negative log of both sides of the equation and solving for negative log of hydronium, we end up getting an equation that says, I'm going to use a different color ink here for you. It ends up saying that the pH of a buffer solution is equal to the pKa value, the negative log of the Ka, plus the logarithm of the concentration of base over acid. Now there's an analogous form of Henderson-Hasselbalch equation that starts with the pOH, and it's equal to the pKb plus the log of the conjugate acid concentration over the base concentration, and it's derived using the Kb expression like this. So using the Henderson-Hasselbalch equation, if we had simply said, hey, this is a buffer, we could jump right to this equation and say the pH will equal the pKa, so the negative logarithm of the Ka value, 4.74 in this case, so negative log of 1.8 times 10 to the minus 5, plus the logarithm of the base concentration, which was 0.244, over the acid concentration, which is 0.100. And when we evaluate this, 4.74 plus the log of 0.244 over 0.1, we get 5.13 as our answer. So there's two ways to find the pH of the buffer solution. One is this sort of long but familiar method of using an ice table and either the acid equation or the base equation. If we had used the base equation, we'd have a Kb expression down here, the pOH, and then the pH. Or jumping into the Henderson-Hasselbalch equation, which is used only for buffer solutions. recognizing you've got a buffer solution, you could use this equation to find the pH much more directly. All right, suppose we want to create a buffer whose pH is 4. The question is, suggest an acid and a salt, or a base and a salt, to create the buffer at that pH. Well, the key in this question is that to recognize that when you want to create a buffer, you want to choose an acid whose pKa value, looking at the Henderson-Hasselbalch equation, one whose pKa value is close to the desired pH value. The reason for that, if these concentrations in the Henderson-Hasselbalch are equal, if your base and acid are equal in concentration, then this will become the logarithm of 1. If it's the log of 1, it becomes 0. So when you have equal concentrations of base and acid in your buffer, your pH is equal to your pKa value. The further away from the pKa value you'd like the pH to be, the greater or smaller this ratio has to become. If you want a pH much larger than the pKa, then you need this ratio to become quite large. If you need a pH value much smaller than the pKa, then you need this ratio to be very small. The problem with that is one of two things. You might run into solubility problems. You might need such a high concentration of salt that basically it exceeds the solubility of the salt. Alternatively, you might end up having such a small concentration of acid or salt that effectively you don't have anything there now anymore. So if you've got 0.000001 molar acid, well, essentially you don't have any acid in that buffer, and its ability to buffer is then very, very, very small. So really you need to have a pH value close to the pKa value so that this ratio in Henderson-Hasselbalch ends up being a reasonable ratio. So if I want a pH of 4, I want to choose an acid whose pKa value is close to 4. If the pKa value is close to 4, then I want an acid whose Ka value is close to 10 to the minus 4. So looking on this Ka chart, something close to 10 to the minus 4 would be anything in this range here. So I could use hydrofluoric acid, whose Ka value is 7.2 times 10 to the minus 4, nitrous acid, 4 times 10 to the minus 4, formic acid's looking pretty good, 1.8 times 10 to the minus 4, benzoic acid would be quite good, 6.4 times 10 to the minus 5 is getting close to 10 to the minus 4. Oxalic acid might be pretty good. Even acetic acid might work as well. So you want to choose an acid whose pKa is close to 4. Of those choices, I'm going to suggest formic acid, whose pKa value is, let me see, so negative log 1.8 times 10 to the minus 4 is 3.74. Okay, so choose an acid whose pKa is close to the desired pH. Now, what salt would I use for this? Well, any soluble salt. So soluble salts start with maybe sodium or potassium. They start with alkali metal cations usually, and alkali metal cations are also neutral ions, so those are good choices. So how about formic acid with sodium formate, so sodium HCOO. All right, so formic acid HCOOH, and sodium formate would be the salt that I would use with it. If you want a buffer at pH 10, then we want an acid whose pKa value is close to 10. So looking at my list here, pKa is close to 10 would mean the Ka is close to 10 to the minus 10. So that would be anywhere from here, the hydrogen carbonate, any of these guys here would be good. Ammonia looks like it would be a good choice, where the ammonium ion is the acid there. So ammonium ion. Now ammonium is the conjugate acid, so I'm going to make a salt with this. So how about ammonium nitrate? Nitrates are soluble salts, and nitrate does not affect pH. So there's the conjugate acid, and the base would be ammonia. Okay, so ammonia, where the pKa value of ammonium is, let me just look at that, it was 5.6 times 10 to the minus 10, so negative log of that is 9.25. So ammonium ions have a pKa of 9.25. Now notice, if the pH that we wanted is 10, we could note here that the pOH that we want is 4, right? pH plus pOH equals 14. If you want a pOH of 4, then your pKb value should be close to 4. And if you look at the pKb value of ammonia, you'll find out that it's about 4.74. It's pretty close to 4, so that would be a good choice as well. All right. Some problem solving. Suppose we want to make a buffer at pH 4.50. We want 2 liters of it. We're going to use 0.25 molar benzoic acid, and we want to know what mass of potassium benzoate should we dissolve to make this buffer. So there's the acid, there's the salt that contains its conjugate base. How much of that salt should we dissolve to make the buffer? So I'm going to use Henderson-Hasselbalch, the pH equals pKa plus the logarithm of the benzoate concentration, C6H5COO minus, over the benzoic acid, C6H5COOH concentration. So the pH we want is 4.50. The pKa value, I'm going to look up the Ka value for benzoic acid, 6.4 times 10 to the minus 5. So negative log 6.4 times 10 to the minus 5. 4.19 is the pKa, plus the logarithm. I don't know the concentration of the salt, so I'll leave that as my unknown. But the acid I know is 0.25 molar. So now I'm going to go find the concentration of the salt. So 4.5 minus 4.19, I get 0.31 is the logarithm of the base, C6H5COO minus, over the acid, 0.250. So now I've got to undo the logarithm, so I'll take 10 to the power of 0.31 on my calculator, second function logarithm, 0.31 equals 2.04. That's equal to this ratio. So to make the desired pH, I need to have the concentration of salt be pretty much twice as much as the concentration of acid. So therefore, let's just draw a line down here, therefore the concentration of salt will be 2.04 times 0.25 0.510 molarity. So now the question is, what mass of salt should we dissolve? So let's take our volume. We want 2 liters. We'll get rid of liters. We'll switch to moles of salt. We'll get rid of moles. We'll switch to grams of salt. Here's our concentration. We need 0.510 moles per liter. And this is our molar mass. So 1 mole of potassium acetate. Quickly calculate its molar mass. 39.1 plus, let's see, there's 7 carbons. And we have 2 oxygens, and we have 5 hydrogens. So 160.22 grams. So 2 times 0.51 times 160.22, we need 163 grams of potassium benzoate. So if you dissolve 163 grams of that salt in the 2 liters of benzoic acid, you'll have your buffer at pH 4.50. Now there's a bit of an assumption, which is a little bit unrealistic here, that the volume does not change when we dissolve that. Putting 160 grams of salt into 2 liters of the solution will probably increase the volume slightly, but we'll assume the volume stays the same. Alright, 2 more problems here. A student's going to make a buffer at pH 5 using acetic acid and sodium acetate as the weak acid and conjugate base. What ratio of acid to salt should she use in the buffer? So Henderson-Hasselbalch, the pH is the pKa plus the logarithm of the salt, CH3COO minus concentration, to the acid, CH3COOH concentration. Now I notice that in Henderson-Hasselbalch I've got a ratio, but it's the inverse, the reciprocal of the ratio that I want. So if I solve for this ratio, I could then just take its reciprocal to get the ratio that I'm looking for. So the pH that I want here is pH 5. The pKa for acetic acid is 4.74, the negative log of its Ka value, negative log of 1.8 times 10 to the minus 5, plus the logarithm of the ratio, salt over acid. So subtracting, we get 0.26 is the logarithm of this ratio. Oops, CH3COO minus over CH3COOH. And now we'll undo the logarithm by taking 10 to the power of 0.26. .82, and that's equal to the salt concentration divided by the acid concentration. So any solution where the salt concentration is 1.82 times bigger than the acid concentration will give us the buffer at pH 5. Now, there's a lot of solutions that you could make with that ratio. The higher the concentrations of salt and acid, though, in your buffer, the greater will be the buffer capacity. So although you might envision creating a buffer with very dilute solutions of salt and acid, giving this ratio, that buffer solution that you've prepared would have a very, very low buffer capacity with very small concentrations here. So the higher the concentrations of salt and acid in the buffer, the greater the capacity to buffer. When you add acid or base to that buffer, it'll resist quite a lot of added acid or added base to change pH. So now, this is not quite the answer we wanted. We wanted the ratio reciprocal of this. So we'll say the concentration of acid to the concentration of conjugate base is the reciprocal of this number, 1.82. So we get 0.550. Alright, one last buffer question. We're going to create a buffer in this problem in a slightly different way. Chemist wants to make a buffer at pH 9. They're going to do so by adding strong acid, HCl, to weak base, to ammonia, NH3. Now you might wonder, how does that create a buffer? Well, if you write a reaction for this, NH3, the weak base, the ammonia, is going to react with, now, strong acid, HCl, rather than write HCl, I'm just going to write H+. That's the hydrogen ions from the strong acid. Strong acids ionize completely. That's going to create ammonium ions. So initially I had just weak base, but when I start adding the strong acid, I'm going to convert some of my weak base into the conjugate acid. So then I'll end up with a solution of weak base with its conjugate acid. I'll end up with a buffer solution. So So the question is, how many moles of the HCl should I add? Well, let's set up a ice table here using moles. So we have 2 liters of 0.1 molar solution, so 2 times 0.1, N equals C times V. We've got 0.200 moles of ammonia initially. We're wondering how many moles of acid should we add, so let's call that X. And we'll say we have no ammonium initially. This is a neutralization reaction. We've shown in other questions that neutralization reactions have very large Kcs. In fact, this Kc value would be the Kb of ammonia divided by Kw, which ends up being very large. The reason that's important is because we can say this then loses everything, this loses X, and this gains X. The reason I'm losing all of this is because we're not going to add so much X that it's going to be greater than this number. We want X to be smaller than 0.2. So we'll end up with 0.2 minus X and X. And there is our buffer. So now we can jump into Henderson-Hasselbalch. We can say the pH that we want is the pKa plus the logarithm of the base, the ammonia concentration, over the acid, ammonium concentration. And so now the pH we want is 9. The pKa value for ammonium ion is negative log of 5.6 times 10 to the minus 10. So 9.25 plus the logarithm. Now here we have to just note something. This ice table uses moles, right? We used moles here. But in Henderson-Hasselbalch, these are concentrations in this ratio. However, the moles of acid and base, they're dissolved in the same solution. The acid and the base are dissolved in the same solution, so their volumes are the same. If the volumes are the same, then the ratio of concentrations in Henderson-Hasselbalch will be the same as the ratio of moles. Remember that concentration is moles over volume. So if you have a C1 divided by C2, and that's equal to N1 over V divided by N2 over V, if your V's are the same, then they basically just cancel, and you're left with N1 over N2. So the ratio of concentrations is the same as the ratio of moles when the volumes are equal. So since these are dissolved in the same solution, the volumes are equal, we can then say 0.2 minus X, the moles of ammonia, over X, the moles of ammonium. Now we can solve this. 9 minus 9.25 is negative 0.25 equals the logarithm of 0.2 minus X over X. 10 to the power of negative 0.25 will equal 0.562, and that's equal to 0.2 minus X over X. Solving this little equation, we get 0.562 X's equals 0.2 minus X. And so 0.562 plus X, we get 1.562 X's is 0.2. And so X is 0.2 divided by 1.562, 0.128 moles. And there's the answer to our question. So we need to add, therefore, add 0.128 moles of HCl to the ammonia. All right, so there's a slightly different buffer question because we prepared this buffer by adding strong acid to a weak base. This is sort of like getting close to a pH titration problem. So there you have it, some buffer introduction questions. Hopefully that's good for either introduction or a good review.